A very good evening to one and all present here, guys. I welcome you all to the session. I believe everyone is doing great and everything been fine around here. So let's just get started with our session. So yesterday, in the last session, this was the thing what we did actually, right? So where we were actually trying to predict the wipe rate values, right? And then we saw that in our wipe rate values, we actually had issues. Like we just had zeros. Correct, right, guys? Very good evening. Yeah, very good evening. Yes, guys, just help me with that part. Are you guys on the same page like me? Or if you're confused, just let me know. I'll help you. Yes, people, please let me know. Guys, I need responses to continue further. So can I get some responses, please? Okay, I don't know why am I not getting these responses. Anyway, it's okay, no problem. So let me explain it to you guys, like what exactly happened here. Okay, Ronak, that's great. Yes, exactly. Wipe rate values were all zeros. Yes, Ronak, it's okay, no problem. Yes, exactly. That's what I'm trying to explain you guys. Like what actually went wrong in this scenario, like whatever we did here, like what actually went wrong in here. Okay, so the thing is, guys, if you look at your x values here, okay, which I have not shown it to you guys, but let me show it to you guys. Social network ads, right? So let me just load the data set. Okay, so let me just run all the cells. Okay, so anyway, so this is okay. Now basically I have to check this x value, right? So if I give this x value here, you can see that we basically have two columns, correct, guys? We basically have two columns. One column is for age of an individual, and the second column is for the salary. So if you look into these columns, guys, there is some issue with this. What is that issue? Can you just go through it? Like, can you understand like what exactly is the issue here? Because when you're passing the features, right, these are the two features I explained you. Now, whenever you're passing the feature, what exactly is happening is one feature has a range of 0 to 18 to 80, something like something less than 3-digit number. Like it's not even in hundreds. Okay, it's just in tens value. But at the same time, if you consider the second feature, what is the value you have? There, the value actually ranges from 10,000s and it goes until a million. Not really a million. 1.5 lakhs, something like that. Sorry, not a million, but yeah, it goes for 150,000, 160,000 as well, right? So tens of thousands to hundreds of thousands. So this is what you have on the another column, and on one column you just have uh, the values in tens. So can you like understand the difference? Like what exactly is wrong in here? Can you figure it out, guys? Yep. So for that reason, what we do is we go for something called as standardization. Okay, the range of values is different. Okay, not only the size, but the range. It basically have to be of the same format. So whenever you are making the data, your features, you have to make sure that your features are basically in the same criteria. Okay, of the standard form. Okay, and the range should also be almost equal. Okay, if not same, it should be okay. Okay, but here no, it's not a case at all, because at one place you have the values in tens and another place you have values in hundreds of thousands. So it's obviously highly unrelated. So that is the reason why we have to perform a technique here called as standardization. So there are actually two techniques what we can use here. One is basically standardization. Okay. Yeah, data transformation, if you can see, yeah, here we have standardization, and then another one is normalization. So we can use any one of it basically. Okay, so what do you mean by standardization? Standardization is nothing but you get your value x. Let's say we're talking about what do you mean, the age, right? So let me just write it down here. So what was the age? Let's say we are working on the first edge where x value is 19. So that is 19 minus mean of x, like on your x value, like age value, what is the mean age value we have? Let's say the mean age value is 36, 37, whatever it is. Okay, and that is divided by standard deviation. Okay, so have you guys heard of standard deviation? Okay, if not, then I'm going to give you a link. You can just go through it and you can understand like what exactly standard deviation. Okay, so it's represented by sigma, and the value can be like just to understand like how the data is varied. Okay, like what is the range of the data, how the data is varying across every new set of values. Okay, so that is your standardization, and that in this case this might be 3 or 4 something around. So whatever you do, whatever the number you get over here, you basically divide that number, and that number can be in the range from -2 to +2. Okay, so basically your number will get converted into -2 to +2 in case of age, and the same thing is going to happen in case of salary. So at the end, you would have a standardized data like -2 to +2. Okay, -2 to +2 basically. So age and salary, right? So both your age and salary will be in the same range then. Okay, yes, obviously the difference will be there, but not that much, right? So this is basically called as standardization of the data, and this is what we are gonna do now on our columns. Okay, this X column, right? We have to perform standardization. If not, then you have seen what exactly have happened there, correct? So for that, we have to standardize our data. To standardize our data, again, we have to go to sklearn. From sklearn.preprocessing here, and then you have to import standard scaler. Yeah, you have to import standard scaler, and then add a code cell here, and sc equal to standard scaler. Yeah, sc is equal to standard scaler basically. So run this up, and now I have imported standard scaler into this object now. Okay, so now what is the next thing I need to do? I basically have to train my data. I mean, I have to convert my data, right? So what is the data we have? What is the data we have? Yeah, and yeah, one more thing you need to remember, guys. The standardization would only it's better to do it after the split. Okay, so this is basically the recommended way, guys. Okay, so yes, you do have to do this after the split, because if you do it ago, then somehow, yeah, because if something goes wrong, then what happens is, I mean, if you do standardization ago, then what happens is the link of the complete column is associated in your test. I mean, in your variable, right? Even though if you split it afterwards, there will be a relation of like what exactly X test value have. So X train would know like what exactly the value is. Okay, like it will have some hints of X test. So just to avoid that scenario, the best thing for us to do is we basically have to do it after the split. Okay, so and how do you do it after the split? You just have to go with X train is equal to sc.fit transform of X train. And similarly, we have to do it for X test as well. X train and X test. How about Y, guys? Do I have to go for Y train, Y test also? Tell me, do I have to give it for Y train, Y? Huh? Let me know, guys. Do I have to do that? No, we don't. Why? Because Y is itself a single value. You don't have any other relation with Y, right? So it's actually not required to do this feature scaling or standardization on Y, because it itself is a single column. So you never do a standard scaling on a single column. You do it if you have multiple columns, and that too if you have different range of data in your multiple columns, or different basically standard of the data. Okay. So here we are just going to work with X train, X test. So if you want to check now, how does your X train and X test below? You can just check it out. So this is going to be your X train value. And then if you want to check X test, you can also check X test. Yep. Okay, why are we getting a value of -9, -3? X train is equal to, yeah, I mean, I shouldn't get a value of -9, -3. Fit transform. Yeah, that's correct. Anyway, let's proceed further and let's see what exactly happens. So let us just run this thing up once again. Wipe. Okay, and now if you check Wipe, then yeah, we are actually getting a proper results here, right? So if you can see, yeah, we have got one issue over here. Okay, and then here it is 0, and it is 1 over here, and here also it's 1, it's 0. But overall, like the result is good. If you can see, I mean, we cannot count every individual value with our manual process, right? Obviously. So to avoid this thing, what we have is we have got some metrics. Okay, so from sklearn.metrics, basically import from sklearn.metrics, you basically have to import accuracy score, and then there is something called as confusion matrix. Okay, so accuracy score, I believe you guys have already understood it, so there is no guessing points for that. Accuracy score is you just have to provide your original values, that is Y test, and then your pred values. Why did I say original values Y test? Because this Y pred is a result of prediction from X test, and which was the actual results of X test. I mean, in reality, it was Y test. That is why Y test versus Y pred. Okay, and if you check it, yeah, you're gonna get 88.75 as the accuracy. So that is almost 89% of the accuracy. So our model is said to be like it is 89% uh, validated or something like that. You got my point, right? So yes, that is the reason why we were actually getting all zeros in earlier case, because we didn't transform our data properly. Okay, so this is one of the reasons, guys, what I was talking about. Okay, now the next thing is a confusion matrix. So what do you mean by a confusion matrix? So if you look at your confusion matrix here, okay, you basically have you again have to give the same thing in confusion matrix also. The parameter is the same basically. Yeah, so you can see here 52 and 1963. So what does it represent actually? Like 52, what is 52? What is 19? What is 6? What is 3? So basically, the confusion matrix works in this way. Okay, confusion matrix works in this way where these are, let's say, the actual values and these are the predicted values. Okay, I have not drawn it properly. Just a minute. Okay, let me just draw it on my notepad. That would be better. Just a minute. Okay, so let's draw the confusion matrix here. Okay, so this is basically the confusion matrix. Okay, you would have 4 different corners, right? It looks like a Windows icon, but yeah, that's a confusion matrix, believe me. And here, let's say here we have the predicted values, and here you have the actual values. Okay, pred values. Pred values is 10, and this is also 10. So now I'll explain you what do I mean by this. Okay, so let's say our X, we had some input, right? In Y, basically, we had some values. Okay, and then we also had some values in Y pred. Okay, this Y pred was actually tested on X, and then we basically got it as Y pred. So now let's consider the first scenario. Okay, so what is the first scenario here? The first scenario is the Y value is basically equal to 1. I mean, in reality or in actual, the value was 1. And our model also predicted it as 1. So where does it lie? It lies in this corner. Okay, and this is called as true positive. Because above you have the predicted values and here you have actual values. Okay, so this one is basically called as true positive because it's true and the value is also positive, right? Like our prediction is also true and the value is also positive. So that is basically true positive. Correct, guys? Have you understood until here? If I give 1, 1, I get the value over here. Correct? Now, the next thing is, the next scenario is, in reality, the value was positive, but our model predicted it as 0. That means our prediction is wrong. But what kind of a wrong is this? This is in such a way that in reality, the value was 1 and predicted value is 0. So it will fall under here. And this is basically called as false negative. Okay. Yeah. And then the next thing what you have here is the third scenario, let's say, where the value was 0 in reality, and then our model predicted it as 1. So where are you going to have this? You're going to have this over here. That is a false positive because in reality it was not positive, right? So it's just giving us the result as positive, but it's a false positive. It's not like true positive, right? So that is your false positive. And finally, in reality, you had your value as 0 and it predicted also as 0. So what does that mean? That means true negative. Like in reality also it's 0 and even our model also predicted it as 0. So that is actually your confusion matrix. And this is how actually it looks. Okay. Yes, Ranak. Okay, so this is how it looks. Now, if you look into this, this is how it is. But for me, I don't know why it's reversed. For you guys, you might have 0 in ones instead of the zeros and interchanged basically. So that means I have a positive 52 value here, which actually like, where the people have actually purchased the car. And then even our model also predicted it as to be positive. And then 19 cars which were actually not purchased. And our model also like, supported us and it says, yeah, we didn't actually purchase it. Okay? So that is true negative. Then what is the 6 and 3 guys? I told you, right? 6 are the cases where in reality the people have purchased the car, but our model says they didn't purchase. Okay, that is false negative. And then what is the 3 value represents? It represents that in reality it was negative, but our model predicted it as positive. So that is false positive. Okay, so this is how it goes. Okay, guys. And then which one is dangerous? So now basically what happens is, guys, whenever you're working with a classification algorithm, right, what happens is you basically have to reduce type of error. Like, you have two different types of error. One is false positive and another one is false negative. So we basically have two types of errors. So which one is dangerous and which one do we have to reduce it a lot? Okay, so the one which is really like dangerous is this one, false negative. Okay, why? Yeah, you can also find accuracy by using confusion matrix, because on this diagonal you have the values which is correctly predicted. Okay, so what was the total value? 52 plus 19. So do 52 plus 19. How much is that? 71. Correct. So 71 are the correctly predicted values, and 9 are wrongly predicted values. So take the percentage out of this, you will get 88.75. Okay. So now I was talking about the false negative one, right? So why false negative is dangerous, guys? Because let's consider the case of what do we say? I mean, in healthcare, let's say I'm taking an example in a healthcare. So our job or our model what we have created is to detect the cancer, okay, in a cancer patients somehow by using some image classification or by using some any other techniques somehow. But the thing is, when you have actually when a person actually has a cancer and our model is predicting that it doesn't have a cancer, it is a big issue. The same thing goes for COVID also. Let's say you do have COVID, you go for a test and then test comes out to be negative, but this was not true negative, this was false negative. Why? Because you actually had COVID, but it says you didn't have COVID. So what do? The moment when people say, yeah, you don't have COVID, you just wander around and then you are like, nothing's gonna happen to me. And then all of a sudden what happens? Your oxygen level drops and there is a very less chance to save you out, right? So this false negative is deadly. So you basically have to take care with this deadly type error. So this one is the sixth error. So whenever you are working with an medical healthcare kind of a project, you need to understand that every time you have to lower your this error. Okay, so this is basically called as type 2 error, and this one is called as type 1 error. False positive is type 1 error, false negative is type 2 error. Okay, so this type 2 is really dangerous. Yeah, type 1 is also dangerous, but it's okay, not a problem. But type 2 is really dangerous. Okay, so that explains you the confusion matrix. So this is how you basically find out the confusion matrix. Okay, so is that clear, guys? Is that clear until here? Every one of you, please let me know. Yeah, guys, just update me. Okay, but we cannot completely remove type 2 error. Yeah, see, we cannot completely remove the type 2 error, but yeah, I mean, 100% we cannot say like our model is going to be 100% accurate, right? So there might be 1 or 2% of errors, which is like negligible. What can we do? Like, it has to be there, right? So that is what, but our aim should be to reduce those types of errors. Okay. Okay. So fine then, guys. So this basically completes our logistic regression. So we have basically worked with our logistic regression model, right? So now the next thing what we need to work with is basically a different kind of classification algorithm itself. Okay, so this one was one of a type of a classification algorithm, but we actually used the regression formula at the back end, and then we got to see this algorithm. Like, okay, so now the next thing what we need to do here is we basically have to learn about the other algorithms as well. Okay, so what is that other algorithms? The one what we are going to look now is basically called as k nearest neighbor. Yeah, this is basically called as k nearest neighbor. Yeah, or it is also represented as KNN. Okay, so KNN or k nearest neighbor. So what do you mean by k nearest neighbor? So let me just draw a different data. Let's say this is a type of classification. Okay, so these are the two data sets. Okay, guys. Now let's say there are like in this case, yeah, we can just draw a line basically, and then we can divide a data like this one is a negative one and this one is the positive one. The one on the right hand side is positive, the one on the left hand side is negative. We can actually do that. It's not an issue. Okay, but the thing is, guys, but when let's say it's not possible for us to divide a data with a single line. Okay, in that case, we actually have an algorithm which actually helps us to deal with that. Okay, so that is nothing but, let's say I'm drawing a point over here. So I need to figure out like what point is this basically. Okay, or let's say the point is not here. Let's say the point is lying over here. Let's say very nearer to red. Okay, so this is a new entry of point. Okay, now I want to find. Let's say this point is basically point N. Okay, I want to find out now this new entry of point. Where does it belong to? Does it belong to the red category or does it belong to the green category? So which point does it belong to? That is what we need to figure it out. Which class does it belong to? Correct. So the KNN algorithm, what it says is it will just look for its neighbor. Okay, the point whatever you have, it will basically look for its neighbor, and we will basically try to predict it on the basis of who is the neighbor of this n. Okay, so depending on the neighbor of this n, we basically take a conclusion saying, yeah, this algorithm is basically of this type or something like that, basically, right? So, for example, in this scenario, which is the nearest neighbor to your point, new point n? Which one is nearer, guys? If you can see, yeah. So the red one is nearer. So how many observations have we taken? We took only just a single observation, right? Just a minute, guys. Okay. So as I was mentioning about that, guys. So you can see that now the value was only a single value, right? So how many observations we took in this matter? We just took one observation. That is the k value was equal to 1. When our k value is equal to 1, we got a conclusion that this point, the point n, belongs to red class. Did you understand my point? Yeah, the number of neighbors is basically called as k. But now, what if I go with k is equal to 3? Then what happens? If I go and if I find out what are the three nearest values, okay? What are the three nearest value? Then what do we get in response to this? Okay, so now if I'm considering three nearest values, so which are the points which are nearer to that y point, guys? Can you guys tell me? What are the points that are closer to this? I mean, tell me the in sequence. Okay, the first one is obviously the red one is the most nearer one. So the first one would be red. How about the other two points? Which other 2 points are actually closer to this red? Yes, exactly. That was my question. So this one is the first one. This is the second nearest, and even this is the third nearest. So you basically have three nearest points over here. So these are the three nearest point of your x. Okay, out of all the points, these three are the nearest ones. So I'll just write it as green and again green. So now the balance actually changed. So if you take k is equal to 3, we can say that this point actually belongs to, yes, that's correct. It actually belongs to a green category, basically. Okay. So that is your KNN algorithm. That's it. It's a pretty simple algorithm. Okay, in your whole machine learning algorithm, this one is pretty simple one. Okay, so this is how you basically calculate your values. Okay, now the next question which comes to your mind is, how do you basically calculate the distance between this point to this point? Okay, so let's say this point is called 1 and this point is called 2. Okay, let's say how do you calculate the distance in the space or between these 2 points? So how do you do is, the formula is d is equal to, okay, x2 minus x1 the whole square plus y2 minus y1 the whole square. So what do you mean by x2, x1, y2, y1? These are not features and labels, guys. Don't get confused. These are just different coordinates of the points. So these points would have a different coordinates, right? x1, y1, and this point would have a coordinate x2, y2. Okay. Yes, exactly. So we are just calculating the distance, and this formula is basically of Manhattan distance. Okay. This one is basically from Manhattan distance. Okay. So there are Minkowski distance, and then there are Euclidean distance. Sorry, this is not Manhattan. This is Euclidean. Euclidean. Sorry, guys. Yeah, this is Euclidean distance. Okay, so you have Manhattan, you have Minkowski. So if you want, you can also figure it out, like how to calculate the distance, and you can work with that. Okay, so now let me just work with a real world example here. Okay, I basically have a real world example with me. So let us just work with that real world example for our KNN model. Okay, so first we'll compute it with our hands, and then we'll check the same thing in our algorithm. I mean, in our collab basically. So let's say this is what we have, like x1, x2. Okay, and then these are the different number of points, like p1, p2, p3, p4. So we have P1, P2, P3, P4. Okay, and then we have X1, X2, and then Y. Okay, so X1, X2 is nothing but the coordinates I told you, right? 7, 7, and then this is 7, 4, and then this is 3, 4, and then this is 1, 4. So the result over here for 7, 7 is, let's say, bad. Okay, this is also a bad, but these two are basically good. Okay, so this is the provided data set what we have with us already. Okay, we didn't find out this information. We already have this information based on some tests. Okay, like this is a kind of a tissue paper, guys. So and tissue paper have this two feature, and depending on that feature, we classify whether it's a good tissue paper or a bad tissue paper. So this is already classified with some industry standards of tissue industry. We don't care about that. Our goal is, like, if there is a new like a tissue paper in the market which goes by the point 3,7. Okay, you basically have a new coordinates with 3,7. So instead of going through all the testings of this tissue paper, we can basically design an algorithm which will actually tell us whether this tissue paper is going to be of a good category or the bad category, instead of, like, doing all those procedures. So we just have to input the data in our ML model, and then our model would actually tell us whether this is a good tissue paper or a bad tissue paper. Okay, so how do you do that? Yeah, the formula is 3,7. So what are we going to do is we are going to find the distance here. So what is the distance now? 7 minus 3 square 7 minus 3 the whole square plus 7 minus 7 the whole square. That is 0. So 7 minus 3 square is 4 square. That is 16. So root 16 is nothing but 4. So can you guys let me know the values of the rest 3 data? Yeah. Just calculate it and let me know what are the values of the rest 3 data. Just let me know. I'll be back within 2 minutes. Just let me know what are the distances and which are the nearest distance of this point 3,7. Okay, just let me know that information. Okay. So yes, so let's just proceed further with this. And what are the points basically? Uh, yeah, first one is 4, then the second one is 5, okay, third one is 3, and the last one is I think 3.6. Yeah, yes, correct. So this is how the data looks like. Now, out of all these points, we have to figure out which one is the closest one. So let's say the number of k here is equal to 3. Let's say the number of k is equal to 3, because we cannot have the number of k even more than 3 here, right? Because we only have 4 values here. So the minimum value what we have to take is k is equal to 3. So if you consider this, then what are the nearest one, guys? If you talk about the nearest point, so the least nearest is this one, 3, then comes 3.6, and then comes 4. So 3, 3.6, and then 4. So what does this represent? 3 and 3.6 is basically from red, and then this one is basically from sorry, 3 and 3.6 is from green, and this is from red. That is good quality. 3 and 3.6 is basically from good quality. So what we can say is the given tissue paper basically with 3,7 belongs to green category, or sorry, good category. Yeah, it's good, right? Yes. So it's basically belongs to the good category. Understood, guys? So this is what we have done until here. Okay. And yeah, have you guys received your minor project already? Well, I'm not sure. Did you guys receive your minor project? No, right? Fine. Once you get it, I'll explain about that. Okay. Fine, fine. You'll get that in this week, maybe. Okay, once you get that, I'm going to explain you on that topic. Okay. So now let's just proceed further. Okay. So now let's just proceed further and do this exact same thing in our KNN algorithm. Okay. So for that, obviously, we need. Yeah. So let me just create a new notebook. So this one would be called as KNN tissue. I mean, not issue, it's a tissue. Okay, and let me just load the file here. Tissue file. Okay, and now let me give you the data file. No, it will compute everything finally at the end of it, right? It will figure out and it will give you like which class does it belong to. That's it. It will compute everything on its own, and then yes, it will take all the data, like all the input features, and it will check. It will try to find out this new point basically belongs to which closest points, and then depending on that, it will give us the response. Okay. July ML1, right, guys? So data. Here I have to give you the tissue data. Yes, this one is a pure classification problem. So yeah, you have tissue here, guys. So okay, and you can proceed with that. Ritvik, actually, it's not allowed for us to do this, but if you want to be in touch, you can basically find me on LinkedIn and you can send me the request by mentioning that you are basically a part of this program and you want to be added with me, so something like that. Anyway, so let me just give you this file as well. So KNN file. Yeah, this one KNN tissue. No, not get link. I actually want to share it with you guys, right? Yeah, I need to move this. Ritvik is just a name. That's it, the same name what you're seeing on the screen. Fine. So I believe you guys have received the file also. Okay, this KNN tissue file. Whatever the file I was working on, I told you, right? So yeah, I have provided you the KNN tissue file as well. So I believe you guys have also received it. So copy path. The first things first, what we need to do is we basically have to import our data. Okay. So import pandas as PD, and then df is equal to pd.read underscore csv. Okay. Yeah. So that's what you have with you. So this is basically x1, x2, and this is bad. This is good. Right, guys? Exactly the same thing what we have done in the previous session. Yes. Any doubts until here? Please let me know. If you have any doubts until here, please let me know. Is this correct? Is everything correct until here? Okay, it's clear, right? Fine. So now, yeah. So the thing what we need to do here is we have to divide our x and y data, correct? So what is going to be our x data? X is nothing but it's going to be df dot ilog. Okay, and then yeah, df dot ilog, and then all the rows. We need all the rows here, right? So that's why all the rows. And how many columns do we need? I need only first and second column. So what I'm going to do is 0, 1, yeah, 0 and 1 I need. So I'm going to go with 2 dot values. So that is X for you. You can just check it out. That is X for you. And it's already in 2D, so I don't have to do a reshape here. And then if you're talking about Y, then Y would be just 2, not from to 2, just 2. And the parameter is Y here. Okay. So you have got bad, and then good. So this is what you have. Okay. So bad, and then good. Now the next thing is, guys, here the y is actually in categories rather than it's because see, as of now, whatever the data we have dealt with, it was basically in a numerical format. But here you are seeing a data for the first time. It is actually not a numerical numbers, but it is actually of an object, basically, or a string type, basically, right? So what do we do with this data? So, I mean, see, first of all, let us just try and check whether this works or not. If it doesn't, then we will come back to this point and then I'll explain you how to convert this bad and good into zeros and one. Okay, so I'll show that later. I'll show it to you guys later. Okay, and here, what is the next thing now? Train test split. We have to do a train test split. So, is it required, guys, actually, train test split? No, right? We don't need train test because only 4 values. What are you going to train and test? Okay, so the thing is, we have to go for the classifier. So, from sklearn dot neighbors import k neighbors classifier. Okay, so you need a k neighbors classifier here, and now if you need a k nearest classifier, just write knn. Okay, and then import your k neighbors classifier, and then you can see here we basically have to change 2 things. Okay, I mean, it's not mandatory. Yeah, one thing is mandatory because the total number of neighbors, you can see by default the total number of neighbors is basically equal to 5. Okay, so Yeah, the total number of neighbors is equal to 5, and then the metric is equal to Minkowski. So metric, yeah, if you want, you can keep it as Minkowski. If you want, you can keep it as Euclidean, or if you want, you can also change it to Manhattan. So that is fine. It's not an issue with that. Okay. Then what actually is the issue here? The issue is the number of neighbors, right? So here it says the number of neighbors is only 5, but we don't even have a data of 5, right, by default. So we just have 4 data. So what we're going to do is we'll just reduce the number of neighbors to 3. Okay, and then distance, I told you, right? It's up to you. So I'm going to go with Euclidean. So what I'm going to do is I'm just going to type Euclidean here. Yep, that's all what I have. Proceed further, and then knn dot fit. And here in your fit algorithm, what do we have to give? We have to give our x value and y value. So x value is in like x1, x2 in numerical data, and y value is actually not in numerical data. It's actually in categorical data. Let's just see whether it accepts or not. Okay, it have accepted as of now. We don't see any issues. Let's proceed further. Now, what is the next thing we have to do? We basically have to predict our data, right? So how do you predict the data? Same thing, knn dot predict. And then we have to provide the x value. We don't have x test here, but instead of that, we have a tissue paper value, right? So what was that tissue paper value which we were checking for, guys? If you go here, what was that value? 3,7, the point n, right? So that was 3,7. So what do you do here for 3,7? You do this. So knn dot predict 3,7. So this is what you do. You run this up, and now we are getting the result as this is basically from a good area. Basically, I mean, not area, the quality. So the quality is good in this case. So that is what we are having the data set with. Okay. Is this understood, guys, now? So this 3,7, right, guys, it will go and it will check with all the inputs, whatever it has. And then whatever the nearest neighbors you have, I mean, your algorithm have designed an algorithm in such a way that if it puts 3,7, then it will basically let you know the output. Okay, all of a sudden. So at the back end, yeah, this is what the calculation it has done already. Okay, like the distances from this points. So from those points, it will try to predict it whether it's a good one or it's a bad one. Okay, so we are not going to practice it on another data set because it's basically the same thing, right? So instead of that, what I'll do is after this session, I will provide you with different like function. I mean, not actually the function, the different data file. Okay, and you can basically predict your data file with this KNN algorithm. Okay, I'll give you those as an assignment. Okay, guys, is that clear? Euclidean metric is basically Euclidean distance. Okay, that is Euclidean distance, how we have calculated right now, right? I just wanted to give metric as Euclidean, but if you don't want, you can skip that part. You can just go with the default one, that's Minkowski. You don't even have to write. You just have to give one parameter, and that should be enough. Like the number of neighbors is equal to 3. You just give that parameter. That should be fine for you. You don't have to worry about that anyway. Okay. Now the next thing is, okay, here it have accepted that the data was in the what do I say? I mean, numerical format, and it have, I mean, the data was in categorical format, and as the data was in y, it was not an issue for us, because if you have a categorical data on y, it's okay, but if you have a categorical data in x, that's not going to work. You definitely have to convert it into a numerical form, otherwise it doesn't work. So now I'm going to show you how to convert this into integers. Okay, so for that we need another package which is called as label encoder. Okay, so that is from sklearn dot pre-processing, that is data pre-processing. We need to import a label encoder. Yeah, we have to get label encoder, and again the same thing here. You have to import the label encoder, and then y is equal to label encoder dot the fit transform of y. So we are giving the input of y, and then output is also the same variable anyway. So if you give y, then what happens is whatever the first entry you had here. Okay, what was the first entry? It was 0, right? So I mean, sorry, it was bad. So whatever the first entry you have, it will be converted as 0, and then the next category would convert it into 1. Did you understand my point, guys? Here this is 0, so this is also be 0, but then a next category comes. So this category will get the value of 1. This also will get a value of 1. Now what if there was another value here which is okay? Then this okay would get a value of 2. That is label encoder. Okay, so depending on your appearances, it gives that value for that specific appearance. That is, my dear friends, called as label encoder. Okay, so yep. Now if you see y, it would say 0011, correct? Yep, that's what it says. So you can work in either way, anything is fine. Okay. Yes, Sriyansh, you can also get that get dummies function, which I'm actually going to show you in the next project. Okay. You can also use that actually in for a longer run, and wherever like you have 2 to 3 different variables where you have to convert it into like numerical numbers. We actually prefer to go with get dummies method. So I'm going to show you both. I've shown you this. I'm going to show you get dummies. So whichever you feel better, you can actually go with that one. Okay. Yes, Medhanand. But before that, you have to run the predict again. Now it would say good itself because your model is trained on good and bad. But if I run this now it would say 1. Understood? Okay, exactly. No, Harshit, you don't have to submit the assignments. You can just keep it with yourself. If required, I'll ask you, and then you have to submit it. Okay, fine then. So this part is done. Your KNN part is done. I'm going to give you the assignment, and you have to work with that assignment. Okay. Now let's get back to the second kind of a classifier, which is, yes, Harshit, I'm going to do that by tonight for sure, without fail. Okay. Yeah. So the next one, what we'll be working with is basically called as SVM. Okay. Just a minute. Just a minute, guys. Okay. Just a minute, guys. Okay. Fine. So the one what we are going to see today is basically called as SVM, or it is also called as support vector machines. Okay. So SVMs and then support vector machines. So what do you exactly mean by this SVM? Okay. Or a support vector machine. So let us just explain you with a normal data set. Explain it to you with a normal data set. So let's say this is how a data set looks like. Huh. So this is what a data set looks like. Okay, so here you have different classes. You have the negative class, or maybe red class or green class, like previously what we have seen. But now let's say I want to basically classify this data. Like I have to divide this data into two categories. So what I can do is I can basically take a ruler, and then I can basically, yes, I can actually do that. So this is one line where I can divide a data, but I have got other options as well. To divide this data, I have got other options as well. Okay, so let's say not only this line, I'm going to draw several lines which would actually help us to yeah. So this is what we need, and then okay, let me draw another line here. I'll tell you why am I drawing so much of lines. Don't worry. Yeah. So let's say these are the three lines what I have. Like say line number one, line number two, and line number three. So now, guys, out of these three lines, which line actually divides a data in a much more better manner? So if I ask you guys this question, then what would be your reply? If I ask you like which line actually divides a data in a much more better manner? So which one is that? I mean, in a better manner, it's like the best possible way. I know all the three divides our data properly, but which one is the best one? Yes. So I've got most of the responses saying line number two is actually the best divided data. And that's actually correct. Why not one? Why not three? Because you can see in line number one, the distance between two classes is different. Like the distance between this red class and green class is very less. Okay, let's say I want to draw a blue line across this. So that is just a distance between your 2 points. And if you're talking about the three one, then yeah, three one also actually have a good separation, but it's biased on the right hand side. Like it's very close to the right hand side comparatively with left hand side. But if you consider the second line, you can see the data is actually divided at equidistant, and the distance is also more, right? So that is actually the reason. So in support vector machine, what it does is it basically selects the line in such a way that it has a maximum distance on both the sides. Okay, so this is how it's actually done. Okay, so how is it done? Let me just explain it to you again in the next diagram here. Yeah, this is what the data you have, and then okay, so now I'm basically drawing a line here in between. Okay, so this is the line what I have drawn in between, right, guys? But as per our SVM algorithm, what it does is it basically looks for the distance at equidistant. Yeah, as of now, it's not an equidistant because I have drawn this wrong line, not that good. But it's okay. We can consider it. You have to assume it. So please do assume it. Okay, and along with that, what it does is this algorithm, it also draws a support line, a very parallel line with respect to our main classifier line and on the side of either classes. Okay, in both the cases, this line would be visible and we just have to draw this line. Yeah, so this is what our like line looks like. Okay, so this is basically the main classifier line what we have. So we call it as a classifier line, or we also call it as a hyperplane. Okay, what exactly do you mean by hyperplane? I'll just explain you within, I mean, this thing will be clear within, let's say, next 10 to 15 minutes. Okay, so that is a positive, I mean, sorry, a classified hyperplane. Okay, and then here the most important criteria what we're looking for is basically the maximum margin. Yeah, we actually need maximum margin. Okay, so we need basically a maximum margin here, and then you basically have the maximum margin across. So this is basically called as D. Okay, and this is has to be D. This also has to be D, and the total margin has to be 2D. That is the requirement. So the distance, the point should be at equidistant. So these vectors have, I mean, these lines, whatever you are seeing, is based on these vectors. You see this two vector point, right? The last boundary point. Yes, that is why it's called support vector machines. Why? Because these are the support vectors. So based on these vectors, we have decided a support here. Okay, for our classifier. That is actually a concept of SVC, support vector classifier. So we just saw how does SVC works. We are not going to see SVR, which is support vector regressor, which is there actually is possible. So you guys can actually figure this thing out later as well, like what exactly is your SVR. But as of now, yeah, this is how your support vector classifier looks like. Okay, and now if you're talking about the vectors, then these 2 points are basically your support vectors. Just now I told you, right? So if you want to note it down, yeah, you can also note it down that these 2 points are called as support vectors. So note these things down, okay, guys. If not, if you are feeling lazy to note it down, you can also take a screenshot, okay? But just keep a copy of this because otherwise you would forget this. Okay, so these are the support vector, and this one is basically positive hyperplane, and this one is basically a negative hyperplane. Okay, so this one is a positive hyperplane, this one is actually a negative hyperplane. Okay, so this is what you have, and this is how your data basically looks like. Okay, positive hyperplane, negative hyperplane, and this one is a classifier, or we also call it as main hyperplane, right? Maximum margin hyperplane, basically. So yeah, this is what we have. Okay, so this is one of the factor of your support vector machines. Okay, or support vector classifier. So this is one of the features. So what happens is, guys, let's say we are talking about two countries here. Okay, let's consider India and our neighbors, which I'm not going to name them. Okay, definitely. So which is better, like if just by having a border with a single line is better, or having a border of, let's say, 2 kilometers is better? Obviously having a border with almost, like, 1 to 2 kilometers, that is actually better, right? So exactly the same thing what we do in our support vector classifier. So this is one feature, one amazing feature of your support vector classifier. But there is another feature also for support vector classifier, and we are going to see that. Okay, yeah, support vector classifier. So we are going to see that second important feature. So what exactly is that feature? Okay, this one is the one, and the next one is basically, well, let's just draw the same data set. Okay, so this is the two data set. Okay, so this is a data set what we have, and then let's say this is the divider with supports. Okay, I'm not going to draw again with scale, and it's going to take a lot of time, but you got the idea, right? But along with this, guys, it also have an amazing feature, that is, in most of your cases, okay, in most of your cases, guys. Okay, first of all, let me just explain, ask you this question. Let's say this is actually two borders. Let's say, okay, let's just talk about that. This is two borders. Okay, so here we have any two states. Let's say we are talking about any two states in India, and this one is basically Maharashtra, and this one is Karnataka. So let's say. Okay, the above one is Karnataka, and this one is a Maharashtra state. Okay, so if you're talking about the Karnataka state, so let's talk about these 2 points. Okay, now let me just explain you guys. I'm going to note this thing. So you guys tell me, out of these 2 points, 1 and 2, which one is a strong feature of a Karnataka point? Let's say we are classifying people here, and the data which you are seeing also is basically representing people. So which one is more stronger towards the Karnataka side? Like, which person are you going to call a strong Kannadiga? Let's say 1 or 2. Yes, that's correct. Exactly. The second person over here is actually having the strongest features of being a Kannadiga, right? Because they are living on the more interior part of Karnataka, and they don't have any other environment affecting on them. But if you're talking about the person in one here, then this person is actually very close to this Maharashtra border. So actually, this is a fact, guys. The people living in a city called Belgaum. Okay, in Karnataka, there's a city called Belgaum, which is more closer on the Maharashtra border. You would see those people have various Maharashtra features, like Maharashtrian features in their lifestyles. Okay, but they are classified as Kannadiga. Why? Because there might be some features which are more of a Kannadiga. That is why they are classified as Kannadigas. Otherwise, they would have been classified as Maharashtra, right? But no, there are, let's say, minimum of 3 features which is required, and that 3 features is classified with this Belgaum people. That's why they have been called as Kannadigas. If not, they will be called as Maharashtrian. Okay, so this is how the same thing happens in our machine learning algorithm also. Okay. Yes, Medhanand. Exactly. Yeah, these days I really have to avoid that, especially what have happened within this week. So that is the reason I'm not going for the countries options. Anyway, let's just discuss with states. Okay, so basically the thing is, the other algorithms, whatever you have, those algorithms are basically designed on the basis of these features, the strongest features. We just the complete model is based on the strongest features. Okay, yeah, it is basically based on the strongest features here. So if a new entry comes up, then the new entry is basically checked with these points. So if some of the minimum points are classified with this point, then we classify that, yes, this entry is from Karnataka or this entry is from Maharashtra, something like that. Okay, but in your SVM, the concept is different. Instead of going for the strongest features, in SVM, what we do is we go for the weakest feature. And then we try to figure out what are the features present in that. Now, let's say there are these 3 features, which is quite important for a person to be categorized as a Kannadiga. So now, whenever a new entry comes, we will check for these 3 features. If you have these 3 features, then only you will be classified as Kannadiga. Because see, because if you don't even have at least these 3 features, what is the point of being a Kannadiga? Better go to Maharashtra, right? Because you have features of Maharashtra moreover. So let's go to Maharashtra. Yeah, so this is how actually it happens in your SVM algorithm. Okay, if you're talking about, let's say, apple and oranges, same thing. Let's say this is apples and this is oranges. So here, whatever you have on the right hand side are the strongest apples. So we are not comparing now with strongest apple. If you get a new apple feature, let's say these features have, these points have 7 features. Okay, 6 to 7 features basically. Okay, but this point only have 3 features. So now we will compare that new point, whatever we have received, with this apple features. Like, it really have to have this minimum 3 features. If you don't have this minimum 3 features of an apple, it will be classified as an orange. Okay, so that is the second feature of your support vector machines. That is, it basically gives you, the model here is not based on the strongest features, but the model is based on the weakest feature. That is the difference. Rest of all your models are based on the strongest features. Okay, and then it compares a new data with the strongest features. Like, if it has 7 features, then we would accept that, yeah, out of any 3 features out of 7, if you have, then we would accept it. But here we say, no, these are the 3 minimum features. You need to have the 3 features at all. If you don't have, yeah, go to other state or other border, right? So this is what an SVM algorithm do in your like second feature of this SVM algorithm. So if you're going for an internship or a job interview, right, and if you tell them that you know about SVM, this is the question what they are going to ask you, like how exactly SVM is different from other algorithms. So you have to mention all these 2 points. The first, what I have explained you, and the second, what I have just explained you right now. These are the 2 features. Along with this, you also have a third feature, which is basically called as kernel. Here we have different kernels. So what do you mean by different kernels, guys? Let's say you have a data like this. Okay, you basically have a data. Okay, so let's say this is what the data you have, and this is how the data looks like. Earlier, if you have a data like this, it was easier for us to classify the data. Like, this is red, this is green. It was easier to classify. But what if the data is of this form? Then how are you going to design and go further with this kernels, basically? With this SVM algorithm, it's not easier for us to draw the different lines and then figure out the different data. It's not that easy, guys, basically. So what we do is we go for a higher mapping method. Like, we basically map a data. So this is a 2D data, right? So now what we'll go is we'll go for a 3D data. That is, we'll map our data into higher dimensions. Okay, we will do a mapping here, and we will map our data in higher dimension, and our data is going to look like this. The moment when we map it in higher dimension, that is in 3D, then the green data would appear over here, let's just say, and then the red data would appear over here, and in between of this data we are going to have our hyperplane. So this is basically called as hyperplane. Why is it called as a hyperplane? Because it divides your data from above and below. So this one is now lying above, and this one is basically lying below. So this is basically called as your hyperplane. Okay, so initially I mentioned you, right, this is also called as hyperplane. So that is the reason, because it is just not a single line now. It is basically a plane. Okay, so the data, whatever you have above and the data you have below, you can do it, and you can basically map it to a higher dimensions. This is the concept, guys, of converting a 2D data into 3D data, and we can basically figure it out which point is of which category. Okay, but we are also not doing this in SVM. Yeah, the concept is this, but in reality we are not doing this. In reality, what we do is, okay, in SVM algorithm, it's exactly the same thing, but what we do is we basically divide a data, plot a data in case of this Gaussian curve or bell curve. We also call it as a bell curve or a Gaussian curve. And then we apply a formula in such a way that the data lying below would lie over here. The red data would basically lie over here. Okay, and your green data would lie over here. So it gets easier to classify the data. And the trick of this data or the kernel which we are going to use here is basically called as RBF, that is radial basis function, because we are basically going to apply an RBF function here to convert our 2D data into a 3D visualization. I mean, the data won't be in 3D. We won't map it into higher dimensions because, guys, see, it is possible to do that. But the thing is, it will consume a lot of processing power. Like in reality, you won't have a data in just 2D. You might have a data in like say 5D, and then you have to convert it into 10D. So it's basically almost like an like a very difficult challenge to work with that scenarios. So to avoid that, what we do is we basically it also gives us the exact same result. So we go with kernel is equal to RBF, and here the kernel is equal to linear in this cases, right? Where we are drawing it with a linear classifier. Here the kernel is basically linear, and here the kernel is RBF. So that is your SVM algorithm. Yeah, I haven't like explain the mathematical intuition from here because it will just confuse a lot. Okay, and it will consume a lot of time, and then we will lag behind. So that is the reason why I have not explained you the mathematical intuition. But although I'm going to provide you the links, which will definitely help you to understand the mathematical intuition behind this algorithm. Okay, I'll give you this link by tonight. Don't worry. Okay, so yeah, this is what we have done. Now, if you want to do this exact same thing on your Google Collaboratory, we can also do that. Okay, so let's proceed further and do this RBF thing on our Google Collaboratory. Okay, so the data what we are going to use is the same data set here of the social network ads, and here we got an accuracy of 88.75%, right? So let's check up with this, like what's up with this. Okay, so yeah, let's just create a new notebook. Same data set. Okay, guys, there is no change in the data set. The data set will remain same. What do you have to give here? Yeah, SVM or SVC ads. Okay, SVC, support vector classifier. I told you, right? Yeah, M is basically for both. I mean, M is basically the concept, but the one what we are using is a classifier, right? So you have classifier and retracer both. So you can call it as SVC or SVR. So this one what we are doing is SVC, that is support vector classifier. Okay. Yeah, let me just add the data set here. Social network ads. Let's just add this. So first things first, let's import pandas. And then df is equal to pd.read underscore csv. So you just go with df, and this is what your data frame looks like. Okay, again the same values. If you want, you can convert the gender column. Now you know how to convert the data, right? So you can basically proceed further with converting the data. But as of now, I'm not going with converting the data. I'm just directly going with age and salary. That's it. Okay. So X and Y, we're going to take this from the previous part. It's actually the same thing. There's no difference in that. But again, guys, you can see the data is not standardized. So we do have to standardize it, but after our train test split. So first we have to get our train test split. So from sklearn.model selection, okay, import train test split. Okay. Yeah, I have not located this data, right? So let me just locate this file for you so that you guys doesn't get confused. Yeah, here it is. So I have to move this. What's our folder? What is your July, right? Yeah, July ML1. ML, I've given KN tissue. Okay, great. Let's move. Yes, so guys, here you're gonna see SVC as well. Okay, so this is the one. So don't get confused from where I got this and all. So basically, train test split. You've got X, you've got Y, and then the test size. Test size again 20% maybe. Yeah, it's up to you. And then random state. If you're gonna go with a random state is equal to 0. And then the next thing what we need to do is we basically have to go with xtrain, and then xtest, ytrain, ytest. Okay, so this is what the data we have. Okay, we have divided our data properly. Now the next thing is we have to transform our data, like standard scaling, right? This week it's okay, no problem. We can just go through the videos, whatever we have gone through it, and then the project discussion is not done yet. Maybe we'll do it in the next session. That is day after tomorrow, right? So yeah, what do we need now from sklearn? Yep, from sklearn dot pre-processing import standard scalar. Yeah, standard scalar, and then you basically have to get this thing done, and then finally extrain y train, right? So whatever we have done earlier, the same thing. So control C, control V, extrain X test. Okay, so it's done. Now what is the next thing, guys? Next thing is we basically have to let me just check extrain. Are we getting the same extrain here? Yes, it's the same thing. Anyway, okay, what is the next thing? Now next thing is we have to import our SVC, right? So from sklearn.svm. So the main algorithm is SVM, I told you, right? Now we need to import either SVC or SVR. As you can see, we have both regression and classification. So we need classification here. So that is SVC. Okay, so support vector basically. Now the class name itself is SVC, but I'm going to write my object name in a small lower cases. That is SVC in lowercase, and then I'm going to say SVC is equal to nothing but SVC, and then the kernel. You can see here, guys, you just have to mention the kernel here. So by default it's RBF, but let me just explain it to you what is the difference. So let's say I'm going with linear, and then the random state over here is also has to be the 0. So proceed further, and there you go. So this is your SVC. Now what we have to do is SVC dot fit algorithm. So I just have to fit my data. So what is the data? I need to fit X train and Y train. So this is what I need to do. And there you go. So our model is ready. Our model is trained now. So if you want to predict it, what do you have to do? SVC dot predict basically, and X test, right? So X test variable, and this variable would be called as Y print. So pretty same stuff, right? So this is basically your Y print. Let's check Y print. Yeah, zeros and ones. It makes sense. And Y test. Yeah, it almost looks like the previous case, right? Let's check the accuracy from sklearn.metrics basically. Import which accuracy? Yeah, I need both accuracy score and confusion matrix. So you can take any one of it. Okay. I mean, both also is fine. It's not like you can just have to go with one itself, and then you have to give Y test and then Y print. So what is the accuracy score? Again, 88.75. Okay, but now let us just check with when SVC is basically, I mean the kernel SVC1. Let me just write it as SVC1. The kernel is equal to RBF. Okay, and then SVC, the same thing. Let's do the same thing. Control C, Control V. Okay, here SVC1, because SVC1 is for RBF. So we are creating a new model now, and then the same goes for predict also. Okay, this will be called as YPRED1 and SVC1. Okay, so that is actually your YPRED1. Okay, so now we can basically go for the accuracy score again. And if you look at this accuracy score now, what is your Y test? Y test is Y test, no change in there because that is the original values. And now the predicted values for RBF is YPRED1. It's not only YPRED but YPRED1. So if you consider this, there you go. So you get a 94% accurate model, guys. So if you go with like SVC of RBF, you get 94% accuracy in this case. And if you go with logistic regression or linear support vector, you're going to get the same output. Okay, so that is basically your support vector classification. Okay, so learn about the mathematical intuitions of this. I'm going to give you the link. You can actually proceed with that. And then the second thing is I'm going to give you some practice data sets as well tonight. Okay, so you guys can actually practice on that part. Okay, so yeah, now we are remained with only one classifier, which is called as decision tree classifier. Okay, once we are done with decision tree, we will be left with the unsupervised learning, that is clustering. Okay, so decision tree clustering is remaining, and then natural language processing part. So yeah, please practice all these algorithms, whatever I have given it to you. Please practice it again, write it down on a piece of paper, try to mimic whatever I have explained it to you, try to watch this recording again so that you would understand it exactly how is it working. Okay, so if you have any doubts or concerns, you can ask me. Otherwise, we'll just wrap this up. Okay, so today the session was of 2 hours, and from now on, this is how the timing is going to be. Okay, from 5 to 7. So 5 to 7 today, and then 5 to 6, I think, on Thursday, right? Harshit, actually, that's not on me. Actually, I don't have any control of that. The only thing what I can do is I can request the team, the operations team, to do this, and yeah, they'll try to do that. Okay, but I'll request them to get this recordings done by tonight. Okay. So fine then, guys. So meet you day after then. Okay. So if you have any concerns, any issues, you can drop me the question. Otherwise, we'll meet you the day after. Okay. This course would run for another, I believe, yeah, 1 more week for sure. Okay. By next week, Thursday, we'll try to wrap it up. If not, then we'll take some extra classes on weekends, and then we'll wrap this up. Okay. Fine then, guys. Mini project, yeah, you will get the data within 1 or 2 days. Okay, for sure. Yep. Fine then, guys. Thank you. Thank you so much. Good night. Bye bye. Take care, guys. Thank you. Thank you so much. Bye bye, guys. Take care. Thank you. I'll add the data set. Okay. Don't worry.